So we're moving on to chapter 3 and chapter 4 now. So uh, the way my slides are broken up in the two chapters isn't identical to the way that the OER book breaks the information up. So I'm just calling these two sets of slides chapter 3/4. It'll cover all the topics that are in chapters 3 and 4 in the text, but I think not in exactly the same order. So in this video, we'll deal with some of the basics, kind of dissect a chemical equation, make sure all the terminology going along with the chemical equation is making sense, and then we'll start to see some calculations that we want to be able to do using the periodic table. So the topic for both chapters is stoichiometry, and that's just the chemistry way of describing any calculations we're doing using chemical formulas or chemical equations. So one of the major goals in this chapter is to be able to work with a chemical equation and use that chemical equation to predict the amounts of products that we're going to form. And in order to do that, one of the key parts that we're going to need to keep in mind is something we already saw in the chapter 2 slides, the law of conservation of mass from Lavoisier, which this is pretty wordy, right? Basically, it's just saying that matter is neither created nor destroyed during the course of a process. So if we know how many grams of reactant we have going in, then we can also predict the number of grams of product we're going to expect at the end. And that'll be a really important part of what we do later on in this chapter. So we've looked at chemical equations a little bit before, but we want to talk about them in a bit more detail here. So what we've got here is a balanced equation describing, in this case, the combustion of the molecule CH4, methane. Combustion just means igniting in the presence of oxygen, so that's what we're observing in this particular reaction. Below the balanced equation is just a visual showing the different molecules. That's not something you typically need to do, but it's another way to visualize that the number of each atom type is equal on the left side, the reactant side, and the product side. So you can see down below here, we just have the numbers of atoms of each type for each species, taking into consideration this coefficient in front of the oxygen molecule to tell us that we have 2 of those. Same for the water molecule, telling us that we have 2 of those. But altogether, if we look through our balanced equation, there's 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens total on each side. So some of the terminology that we want to make sure we're feeling confident with, we'll take a look at in just a second here. The numbers out front are coefficients, and the numbers that are subscripts after a particular atom, those are just called subscripts. So if it's out in front, it applies to the entire molecule that follows it. If it's a subscript, it just applies to the atom that it comes right after. So what we have on the left, the species on the left are always going to be the reactants, and that should make sense, right? Those are the things that are reacting. And then what we have on the right, the things we're making or producing in our reaction, those are called our products. So reactants on the left and products on the right. Something else that we probably talked a little bit about before is following each molecule, you see a letter in parentheses, and that's telling me the chemical state. So in this chapter, we're pretty much going to see S for solid, L for liquid, and G for gas. I think in my example in chapter 5, we saw AQ for aqueous. We'll see that a lot more in the next set of slides. That just means that it's something that's dissolved in water. So those are the 4 different options we're going to see for states. SLG, or AQ, like aqua for aqueous, meaning dissolved in water. And I think I already said this right. The coefficients are the numbers that come out in front of the entire molecule. And you can kind of think about it as just applying to the entire formula to say there's two of that entire molecule. So coefficients are what we're going to use when we balance equations. Subscripts are kind of built into the original formula, and those are not things that are going to change. So later on in this chapter, we'll talk about balancing equations and get into that in a bit more detail. So again, just to clarify, subscript versus coefficients, the 2 here only applies to hydrogen, and that's the complete chemical formula for water, H2O. That's different from the 2 out front, like we were talking about. That's our coefficient that's applying to the entire formula. So some people like to think about that entire formula in parentheses, and the 2 is applying to that entire thing. So one of the first calculations we can do using the periodic table, and I think there's a newer periodic table under the handouts folder that's a little bit easier to read in terms of the numerical values. But one of the first things we want to be able to calculate are formula weights. So formula weight is just simply the sum of the atomic weights for the atoms in our chemical formula. And if you remember in chapter 2, we started to talk about isotopes, and so the weights that we observe for these atoms, those are the weighted averages based on the naturally occurring isotopes. So when you see that they're not exactly whole numbers, that's the reason for it, that it's taking into account the naturally occurring isotopes. So something like calcium, if we round to 2 decimal places, which that's just going to be something we're going to pretty much follow as a general rule, we get 40.08. And that's presumably because the primary calcium isotope weighs 40 AMU, and then there's another one that weighs probably 41. With chlorine, you see we're nowhere near a whole number, right? It's 35.45. Something like chlorine is kind of a classic example where more or less, and this isn't perfect, chlorine is about 75% chlorine 35 and about 25% chlorine 37. So that's the atomic mass number, right? So that's the sum of protons and neutrons for these atoms. So those aren't exactly what we have. It's a little bit different than that. I think there's a little more chlorine 35, but the weighted average gives us that 35.45 AMU. All right, so in this question, we're just being asked, I guess it's not really a question, just an example, but in this example, we're trying to figure out the formula weight for calcium chloride, CaCl2. Pretty straightforward, right? There's 1 calcium, so I add together the average weight of 1 calcium atom, and there's 2 chlorine, so I multiply the average weight of chlorine by 2, just combine those together, and we get 110.98 AMU. So again, as a general rule, without really any rhyme or reason to it, I'm just going to say let's round our atomic weights from the periodic table to 2 decimal places, and if you follow that, then it'll just give you one less thing to worry about, just kind of always collecting that value to 2 decimal places. A not especially important distinction that we're going to see here is generally formula weights are reported for ionic compounds. So ionic compounds we understand a little bit, right? It's two oppositely charged species that are attracted to each other. Those are the things that we spent lots of the second half of chapter 2 naming, and technically for ionic compounds we call it formula weight, and for molecular compounds, we call it molecular weight. Nothing in the process changes at all, but that's technically the distinction that we make. So probably I'm always going to end up saying molecular weight since we're talking about molecules, but it really doesn't matter what that terminology is. So here it's asking us to figure out what the weight would be for the molecule C2H6. So pretty straightforward here, right? There's 2 carbons, each one weighs 12.01 atomic mass units. This one is because I think 99% of carbon is carbon 12 and 1% is carbon 13, plus a couple other things. So we more or less get 12.01. And then for hydrogen, there are 6 of them, and each hydrogen to 2 decimal places is 1.01 AMU. So if we add that together, then we'll get an overall weight for the molecule of C2H6. Okay, one other fundamental calculation that we want to be able to look at will be getting the percent by mass. So we'll take a look at that in just a second. I think normally this is just one more example for us to work through for the ionic compound calcium phosphate. So I just wanted to look at this example since we have a polyatomic ion, so we just want to be clear that if there's a subscript after the parentheses for a polyatomic ion, that's going to apply to the entire portion that's in parentheses. Still a subscript, not a coefficient applying to the entire molecule, but it is applying to everything that's in the parentheses. And you saw that earlier on when we were doing naming. Just want to make sure we're applying it appropriately when we're trying to calculate the mass of our molecule. So if it's PO4 parentheses 2, then we want to understand that that's 2 phosphorus atoms, and now 4 times 2, 8 oxygen atoms. All right, so 3 calciums, each one is 40.08. 2 phosphorus atoms, each one is 30.97. And then 8 oxygen atoms, each one is 16.00. Then we add it together and get 310.18 AMU. So really the first of true calculations we're doing using the periodic table. I'm sure this is pretty straightforward, but just want to make sure it makes reasonable sense. Okay, let's look at one more slide to talk about calculating percent by mass, and that'll be it for this first short video. So, or percent composition, kind of the same thing. So, percent by mass. So what we're interested in talking about is the percentage of the mass of a compound that comes from each of its elements. So it may seem kind of strange or not really have any purpose to it to do this sort of calculation, but later on we're going to flip this around, and rather than calculating the percent by mass of each element from the formula, we're going to use the percent by mass from each element to figure out what the formula actually is. So it makes sense to me to figure out how to do this because later on we're going to do kind of the opposite of it. All right, so there is a formula here to look at, of course, but relatively straightforward in terms of what we're actually trying to do here is just to figure out how much each atom is contributing to the overall mass. So in the denominator, we have the overall formula weight of the compound, so you're still going to need to add it together for the total, but in the numerator, it's just the fraction that's contributed by the particular atom. So we can just figure out the total mass, put that in the denominator, and then in the numerator will just be the partial mass from whichever element it is we're talking about. And to convert it into a percentage, right, we always want to be sure that we multiply by 100 in order to do that. So let me show you one example of this, and that should pretty much do it. So in this particular case, we're working with the chemical formula C2H6O. If we total this up, I think you really get 46.08, but with all my rounding, I didn't get it to add up to 100 without doing it like this, so the process is going to be the same. So you can see for each calculation, the denominator is 46.07, the total mass of the molecule. And then depending on what it is I'm talking about, carbon, there's 2 carbons at 12.01, or hydrogen, 6 hydrogens, and again, I just made it work, so 1.008. We'll stick with the plan of 2 decimal places in general. I just wanted to make it add up to 100 so it wasn't weird. And then oxygen, there's just 1 in the formula, but 16.00. And so when we combine all of that together, in each case, we're figuring out the percent by mass for the individual components. So for carbon, we get 52.14, hydrogen 13.13, and oxygen 34.73. So in this case, I gave you the formula C2H6O, and then you told me the percent by mass for each component. But what we want to do later on is the exact opposite. We want to be given these percent by mass values for carbon, hydrogen, and oxygen, and use that to predict the chemical formula. So usually the first time students see percent composition, it seems like kind of a weird exercise to be doing, but ultimately, probably not in the next video, but the one after that, we'll flip this problem around, and then understanding how percent composition numbers are determined is going to be really helpful in figuring all of that stuff out. Okay, I think that's good for this video. I think this corresponds to the first homework assignment for chapter 3 and 4 in Chem 101. So we'll stop here and then pick up with slide 17 in the next video.